Why is it that during winter it's not uncommon to have days with abnormally high temperature and summer-like weather, but in the summer it never drops to winter-like weather for a day? Lots of incomplete answers here. Take a look at this graph of solar intensity versus latitude. As you can see, the summer pole receives about as much sunlight as the equator, actually, slightly more because of the 24-hour days in the Arctic Circle. On the other hand, there's a huge difference in energy provided to the equator versus the completely dark winter pole. As a result, there's a huge difference in temperature between the winter pole and the equator, and not so much between the summer pole and equator. But that just explains changes in temperature versus latitude, not changes over time. So let's think about weather systems. Storms are created by the north-south temperature gradient. As heat moves from equator to pole, a small amount of it is converted into kinetic energy. Heat flow causes motion, just like a very inefficient steam or gasoline engine. When the temperature difference is large, the engine runs faster and more efficiently, creating more kinetic energy, which is to say the storm winds blow stronger when the pole-equator temperature difference is large. So, in the wintertime, the difference in solar heating creates a much larger equator pole temperature difference than in the summer. This creates much stronger wind patterns. So you've got stronger winds, blowing a bigger temperature gradient around across the surface of the Earth. So you see much bigger temperature shifts from day to day. If we could travel at 99.9% the speed of light, it would take 4 years to get to Alpha Centauri. Would the people on the spaceship feel like they were stuck on board for 4 years, or would it feel shorter for them? The time dilation factor is the square root of 1 minus f squared, where f is the fraction of light speed. This means that the time that passes inside the ship approaches 0 as f approaches 1. If you could travel arbitrarily close to light speed, you would experience the journey as effectively instantaneous. At 0.999 c, which is 99.9% of light speed, it calculates that time is slowed down to 4.47% of the outside value. That means 4 years are experienced as approximately 65 days. This is literally the time that passes for the ship. It affects everything, from atomic clocks to metabolisms to brain activity. Do giraffes get struck by lightning more often than other animals? Four-legged animals are more vulnerable to lightning strikes because ground current has high chances to go through vital organs. It also describes how large animals such as giraffes and elephants have higher chances of deadly strikes. There is the obvious thing about the fact that they are tall, so even under a tree there is a non-negligible chance that lightning could jump directly to their head. The other less obvious one is that even if they are not directly hit, the large distance their legs span increased the voltage and potentially the current going through them as described in this figure. Sadly, the article lacks hard numbers on strike frequency depending on the species. Giraffes getting killed by lightning is not that uncommon. Between 1996 and 1999, the Rhino and Lion Reserve near Krugersdorp, South Africa, had 2 of its 3 giraffes killed by lightning. The third animal, a juvenile, was also struck but survived. Betsy the giraffe was killed by lightning at Walt Disney World in Florida in 2003 in front of lots of witnesses. What percent of my weight am I actually lifting when doing a push-up? Researchers found that the answer depends both on the variant of the exercise as well as the stage of the exercise. For example, in a traditional push-up the number is about 69% in the up position at the top of the movement and 75% in the down position bottom of the movement. It's also worth mentioning that the study also looked at a modified push-up. This modification, as shown here, is essentially just an easier version of the exercise where the knees stay on the floor. Surprisingly, to me at least, even in this simpler version you still lift quite a bit of your body mass, 54% in the up position and 62% in the down position. What is the point of using screws with a Phillips head, flathead, Allen, hex, etc. instead of just having one universal screw type? The reason for the different styles is cost and torque. The slotted head screws are cheap and easy to make, but they're completely useless for powered screwdrivers, and you can put much torque on a screw without it either slipping out or stripping the head and marring the surface of whatever you're screwing. Phillips screws are self-centering, making powered screwdrivers possible. They're somewhat more expensive to produce than slotted head. They tend to cam out easily under torque, making it hard to apply much torque. I've heard they were designed that way to prevent over-tightening. However, it's not good for exposed fasteners to look stripped. Robertson head and Allen head fasteners can handle more torque than Phillips head fasteners, but are more expensive because the bottom of the hole is flat unlike the pointed end of the Phillips. There's more contact area and so it's less likely to cam out. The Robertson head is cheaper than the Allen head, but the Allen head has 6 points of contact rather than 4, making it less prone to rounding out the hole. The Torx head fasteners solve the problem of rounding stripping by having the flat bottom of the Robertson Allen that reduces cam out, but it is much better contact with the driving bit to prevent stripping the head. The points of the star on the driving bit engage the recesses on the screw at nearly right angles, so it has a very positive contact. Torx is becoming more and more popular because of that, particularly in assembly line work because they're less likely than a Phillips to be damaged when tightening. The Allen internal hex heads are often used for exposed decorative fasteners on some assembly-required furniture. It's also very cheap to make the Allen keys, so they usually include one with the fasteners. If hand sanitizer kills 99.99% of germs, then won't the surviving 0.01% make hand sanitizer resistant strains? Most hand sanitizers use alcohol, which kills indiscriminately. It would kill us if we didn't have livers to filter it, and in high enough doses will kill anyway. Some germs survive due to randomly being out of contact, in nooks and crannies and such, not due to any mechanism that might be selected for. Let's say you throw 1,000 humans into a volcano. One of them happens to land on a ledge inside the volcano and escapes. If he has kids, they will not be volcano resistant. Do heavily forested regions of the world like the eastern United States experience a noticeable difference in oxygen levels, air quality during the winter months when the trees lose all of their leaves? Yes. Here is an excellent map showing accurately modeled atmospheric levels of CO2 from satellite and ground measurements taken during a year. For example, you can easily see humans emitting it, and then forested regions sucking it up unless it winter in that hemisphere, in which case it just swirls around until spring. Other gas levels show similar seasonal patterns. Does the size of a creature, or the size of its eye, affect what can be seen by the naked eye? For example, can ants see things we consider microscopic? Are ants microscopic to elephants? In terms of optics and photoreceptor density, which are the principal factors in a creature's visual resolution details per degree of visual angle, there probably isn't much real difference between the angular visual resolution of, for example, a jumping spider and a house cat. Both can see, at best, about 10 details per degree. So if you shrank a cat down to spider size or vice versa, they'd both have similar limits to the smallest things they could see. But since they're different sizes, the sizes of the things they can see will also scale. Since the eye is getting smaller, its near point, I think I meant depth of field here, is getting proportionally shorter. So if a jumping spider's eye is 1,000 times smaller than a cat's eye, it can potentially resolve details that are 1,000 times smaller than what a cat can resolve. A cat can never get optically close enough to a grain of sand to make it a degree wide, so that it could see 10 details on its surface, while this optical distance is easily available to the spider. The caveat to this general scalability of vision is in the noisiness of light, that is, factors like diffraction limitation in how small of a point can be focused, or chromatic aberration, the difference in focal distance for different light wavelengths for a big eye with a big pupil. This noisiness is insignificant, but for a spider's eye it is getting significant, since all of us are looking at more or less the same light bandwidth. Jumping spiders, for example, deal with this by having retinas at different focal depths to try to account for chromatic aberration. But this stuff gets complicated, especially considering that the range in optical quality and photoreceptor density across species washes out most of these limitations. I think you could safely suppose that, in the range of terrestrial creature sizes, vision basically scales with size. Why do we have to fall asleep? Why can't we just decide to be asleep? Sleeping literally changes our very physiology. Our core body temperature drops, which allows certain proteins to work differently than they do during our waking temp, As a broad example, it's not something we'd want easy control over. Most importantly, the process of getting sleepy is highly regulated by not only our circadian rhythm but also by other hormone systems. We need to burn energy to feel fatigue when we use ATP and make adenosine as a byproduct, which signals fatigue in humans. We need a lack of blue wavelength light to initiate the process of releasing melatonin at night, which makes us sleepy and helps initiate the sleeping end of our circadian processes. We don't have voluntary control over sleep because it's chemically regulated. Adenosine, melatonin, hypercretinorexin, etc. It's not something we can flex like a muscle. It's essentially hormonal in nature and therefore requires us to use drugs, meaning ligands that bind to targets in our body to control it. For humans, seawater is not drinkable due to its high salt content. How do whales, manatees, seals, and other seafaring mammals stay hydrated? The short answer is A. They get water from their food, and avoid salty food. B. They may have modification to their kidneys to allow them to excrete more salt. C. There are a lot we don't know. Marine animals are hard to study,